Hi everyone, we are Group 6 from Chemical Engineering Thermodynamics Section 1. Our lecturer is Dr. Aisha and our topics is Flash Separator Design for Ethanol and Chloroform. Our group member consists of Teo Jianxun, Teo Gajian, Noh Fatin and Ong Jinjian. The objective of this project is to design a flash separation vessel for a binary mixture of ethanol and chloroform. Flash distillation is a continuous single-stage separation process. A pressurized liquid feed is partially vaporized by reducing its pressure inside a drum. This phase splitting occurs in strict accordance with the thermodynamics vapor-liquid equilibrium established by the operating temperature and pressure. This is the literature review for our project. In real-world behavior, mixture containing lower alcohols like ethanol and solvents like chloroform represent a strongly non-ideal system. It is because the molecular interactions cause significant deviations from ideality, resulting in the minimum boiling azeotrope. So in industry, standard flash distillation cannot perfectly separate these components due to this thermodynamic barrier. But for our project basis, we are assuming the mixture to behave strictly as an ideal solution. This assumption simplified the complex thermodynamics, allowing us to model the VLE directly using Rao's law. Activity coefficients are bypassed, making mathematically phase predictions straightforward and reliable.
I will explain the process and composition conditions used in this flash separation. The operating temperature is set at 70 degrees Celsius, which is between the boiling points of ethanol and chloroform. This temperature allows partial vaporization and promotes separation. Next, the operating pressure is maintained at 1 atm, which is equivalent to 101.325 kilopascals, representing standard industrial conditions. The feed is an equilibrium mixture consisting of 50% ethanol and 50% chloroform. For simplicity, all calculations are based on a 100 mole feed basis. Next, this slide shows the physical properties of ethanol and chloroform used in our calculations. Ethanol has a normal boiling point of 78.25 degrees Celsius, while chloroform boils at 61.15 degrees Celsius. We also use the Anton constant A, B, and C to calculate the saturation pressure of each component at the operating temperature. Since chloroform has a lower boiling point, it is more volatile and tends to vaporize more easily than ethanol.
So now we have to calculate the vapor pressure, which is P set, using the Antoine equation. In order to calculate the vapor pressure, we have to determine the parameters A, B, and C of ethanol and methanol respectively from table B2, as well as the operating temperature in degrees Celsius. After getting the parameters of each substance, we substitute the values into the equation of vapor pressure, which is ln P set equal to A minus B over T plus C. And then we will get the final answer of P1 set, which is 72.5174 kilopascal, and also T2 set, which is equal to 134.2278 kilopascal. After finishing calculating the vapor pressure using Antoine equation, we are moving on to bubble point pressure and dew point pressure. For bubble point pressure is equal to S1 times P1 set plus X2 times P2 set. And we will get the final answer 103.3726 kilopascal. For dew point pressure is equal to 1 over Y1 over P1 set plus Y2 over P2 set, and we will get 94.1628 kilopascal. After calculating the bubble point pressure and dew point pressure, we will get to know about the operating pressure, which is between the dew point pressure until bubble point pressure, which is 94.1628 kilopascal until 103.3726 kilopascal.
And next, we use Rod's law to calculate the coefficient K. The formula for coefficient K is P saturated over the total pressure. Then we get both of the ethanol and chloroform coefficients, which is 0.7157 and 1.3274. Then we calculate the composition in liquid. The formula used is X1 equal to P minus P2 saturated over P1 sat minus P2 sat. So we plug in all the value and we get 0.5332. And the remaining is the X2. So we use 1 minus X1, then we get 0.466x. For composition in vapor, the formula used is Y1 equal to X1 K1. So then we get 0.3816. So this one for Y2 is similar with the previous one, which is 1 minus Y1. So the answer is 0.6184. Then we calculate the number of mole of vapor and also liquid. So for the number of mole of vapor, the formula used is summation of Zi Ki over 1 plus V bracket Ki minus 1 equal to 1. So then we substitute all the values equals to 1. Then we get the number of mole of vapor is equal to 0.2315 mole. And for the remaining is the number of mole of liquid. So we use 1 minus number of mole of vapor, then we get 0.67685 mole.
In conclusion, the simulation confirms that a single-stage flash drum operating at 70 degrees Celsius and 1 atm can successfully separate an equimolar ethanol chloroform mixture. This is because chloroform is more volatile than ethanol. It is enriched in the vapor stream, while ethanol is enriched in the liquid stream. This project demonstrates the importance of vapor-liquid equilibrium calculations in designing and optimizing separation processes in chemical engineering. I think that's all from our group. Thank you.